and this is a new video under the Seismic Design of Structures series, and today I'm going to talk about the ASCE E7 seismic provisions. I'm going to talk about the detailed descriptions, and today I'm going to talk about an introduction for these provisions. Okay, let's go and see what are the topics that we are going to touch upon for today. So first of all, I'm going to give a general introduction for ASCE and the main concepts behind using ASCE, or American Society for Civil Engineers guideline for seismic design and criteria. And I'm going to talk after that about some or the philosophy of design and detailing. And after that, I'm going to explain about the near fault site ASCE provision, which has been added in the new version of ASCE 7.16. Before it was not there, so I'm just going to give the importance of including this or such guideline or provision in the new ASCE 7 guidelines. After that, I'm going to talk about the mapped acceleration parameters, which is S sub S and S sub 1, short period spectral acceleration for short period, and spectral acceleration for at 1 second. So I'm going to talk about it. After that, I'm going to talk about the risk targeted maximum considered earthquake, which is something new, considered to be new. If we're going to compare it to 2005, before we were not talking about risk targeted, but starting from 2010 we started to talk about the risk targeted maximum considered earthquake. So there is a great difference between the two versions, 10 and 5 of ASCE, and I'm going to give some hints about this. And why ASCE 7 spectral approach or spectral maps approach is not used anymore. I'm going to explain about this point. Then I'm going to talk about the site coefficients, FA and FV, coefficients for modification of the mapped acceleration in order to obtain the maximum spectral acceleration. So I'm going to talk about it, and I'm going to talk about what is the importance of inclusion of soil properties and inclusion of the soil deposits in general in controlling the spectral acceleration. And after talking about or obtaining the maximum after multiplication of these factors by the mapped acceleration, we're going to obtain the maximum. After that, we're going to talk about the design spectral acceleration from the maximum, how we can obtain and get them, and the rationale of the 2/3 and so on. So these are like the contents of today's lecture or today's video. I hope that you are going to be interested in what I'm going to explain. Okay, let's go to the introduction. In general, ASCE, it is the American Society for Civil Engineers guideline. It's considered now to be the most important guideline for seismic design and detailing for those who are interested in seismic engineering and seismic design. So we're talking about ASCE, okay, and there is 7, committee number 7, and then after that there is dash, which means that the edition year, whether it is like 5 or 10 or 16, the latest version is 16 till this video. I'm not sure when they are going to issue the new one. Okay, and stands for American Society for Civil Engineers, and there are a lot of different guidelines. Mainly they are coming from, or we can put them under FEMA, Federal Emergency Mitigation Agency, which is one of the most important sources for seismic guidelines. And now most of these guidelines are being included now in ASCE, okay, 7 and ASCE 41, as we are going to talk about maybe in later videos in this series. Okay, so let's talk about the ASCE provisions. They are for seismic design. And mainly they are, we cannot say they are only for seismic design, but they are much broader than determining only the loads. Because many people think that only we are concerned with what are the loads coming from the earthquake, and then ASCE is going to give it for us. But actually, now it is much more broader than only determining the loads. Okay, so we are going to find that there are a number of issues addressed by ASCE rather than or on top of the loading, determining the loading. There are a number of requirements relating to the systems that may be used in high seismic zone. Whenever that we go to high seismic zone, you are going to find that it's not only about loading. We're talking about some other issues. Like if we're going to talk about detailing, for example, what are the detailing requirements for those systems in high seismic zones? Okay, and to structure configuration issues, that whether that we are going to accept regular or irregular frames or irregular configuration or not, and if we're going to accept it, what are the penalties that the code is going to impose upon your design if there are some kind of irregularity in your configuration. So it is not only loading, we're not talking about loading. It is kind of general guideline for many things, including detailing and configuration and so on. Experience has proven that regular structures, means that the structure, the symmetric structures and structure without discontinuities, perform much better in an earthquake than irregular structures. This is actually going to be taken into consideration in ASCE. Therefore, even if a nonlinear procedure is used in design, ASCE 7 penalizes certain irregular structure. And this is an important issue that you're going to find. A great part of our course is going to talk about irregular structures and how we can use our detailed design in ASCE in order to understand first what is the meaning of irregularity and how it will affect the performance, the seismic performance of the structure under consideration. Okay, so we are going to deal with this irregular structure with putting some additional design and detailing requirements. So that's the point regarding the buildings in general, whether they are regular or irregular structure, and how ASCE is going to work with them. Now let's talk about the seismic forces on a structure, how the ASCE is dealing with it. From the structure dynamics, it is known that a number of different forces act on a structure during an earthquake. These forces include inertia forces, damping forces, elastic forces, and an equivalent forcing function. If you remember the equation of motion that I put before, I was like putting one term for inertia plus another term for damping plus another term for elastic forces, and on the right hand side we put a term for the ground excitation, which is including the ground excitation, right? So actually this is the inertia forces here, this is the damping forces here, elastic forces, and here this is the an equivalent forcing function, mass times the ground acceleration, m times the AG double dot of, or the acceleration of the ground. And you can go back to our previous videos to understand the rationale behind this equation of motion. So now the code, we are now not dealing with dynamics, we're dealing with, we want an easy way, an easy approach, okay, for obtaining these kind of loads and putting it in one place together, so that would make it easier for the designer to follow. We're not going to tell the designer every time that you need to know what is the inertia forces, what are the damping forces, what are the elastic forces going to be continued, and you are going to make and put it into an equation. We're not going to go into these details. Rather, we are going to check a simple, straightforward approach for this. Actually, there is a range of approaches has been developed to analyze loads and displacements. This is our main concerns, that whenever that we're dealing with seismic design, we are highly interested in loads, seismic loads, and the displacements that is going to occur in buildings due to earthquakes. Buildings are complex combination of structural and non-structural material. That's right, and very true that we have structural and non-structural materials, all of which influence the response of a structure to seismic ground motion. Okay, so now we are like not only the loads or the forces applied in the system, but also we have like non-structural elements and materials, they are involved. So we need to find an approach that is taking into consideration everything. The purpose of analysis for seismic loads is to make sure that the structure being designed meets minimum strengths and deflection. This is two important criteria that we need to fulfill: strengths and deflection. And this is how our design, or how our the guideline is dealing with the problem. Just putting the minimum strengths requirement as the final goal, and the deflection, you can find sections related to the deflection, and you are not going to exceed this deflection. So now this is actually considered to be one of the limit states, strength limit state, but we have different other limit states which is not considered here in this code. Maybe we are going to design for different limit states. Okay. Here we are talking about some certain limit state, which is strength, life safety limit state, for example. But we have other limit states like immediate occupancy, we have life safety, of course, collapse prevention, and so on. The code does not work for other limit states. Only one limit state is working for it. Okay. Now let's talk about the equivalent lateral force procedure. Okay. So this is one of the procedures that is going to be used. Instead, we said that there are many approaches. We are going to use the equivalent lateral force procedure. Rather than attempting to define all the forces, as we said before, during an earthquake, the equivalent lateral force procedure takes a simplified approach, and this is the most simplified approach. What is the rationale behind the equivalent lateral force method? The empirical method is one that is particularly easy to visualize. The earthquake force is treated as inertia problem only. So we're going to talk about this in the next slide. Okay, inertia force. Before the start of an earthquake, a building is in static equilibrium. Suddenly, the ground moves and the structure attempts to remain stationary. That's the point. Let's have explain it in this small illustration picture. Consider that you are standing in a bus, and the situation when a bus starts suddenly from rest. It was at rest and then starts to move in this direction. What will happen for you? You are going to find that you're going back, right? And if the opposite apply in the case of situation where that the driver is hitting the brakes, so the bus stops suddenly, and you are going to find yourself as jerking to forward, right? This is exactly what's being done for the building. So whenever there is an earthquake that is going to hit the structure, whenever it comes in this direction, the structure like starts to keep its original position, right? Whenever it strikes in this direction. And whenever it comes in the other direction, then the structure is going to, to keep its original direction. Okay, so that's the original status or condition. From here, we are going to deal with the problem in this way. We're going to consider that there is a force that is going to be developed, and then we're going to put like equivalent force on this, equivalent force on the system. Okay, equivalent force on the system. So instead, if this is the base shear that is going to be developed, this means that it is equal to as if that we are applying a force on this mass in this direction, right? So there would be an equilibrium here. This is the philosophy of equivalent static force method. This is what we're going to do. Then what about the damping? What about the elastic forces? What about these kind of issues? We are going to take into consideration all other forces in using some factors, so that we are going to take into consideration what is the system type, whether it is moment frame, bracing, or it is braced frame, or ordinary moment frame, or special moment frame, or whatever, the system itself is going to be reflected in some factors. And similar, we are going to do the same for the deflection, for example. We are going to have nonlinear displacement. Actually, whenever that we apply the force in this way, this means that there is elastic force might happen. We're not dealing with any nonlinearity here, but we are going to consider nonlinearity by using some factors. Okay, so we're going to use some factors to transform the linear displacement that is going to take place to nonlinear one, as we are going to see in the details. Okay, so if you understand this concept, this would give you the idea of the equivalent static force method. Seismic forces are generated by acceleration, as we said, of the building mass. Typical practice is to consider that a lump of mass acts at each story level, and this is right. At each story, we are going to consider that there is mass is lumped in this story. So we have a multi-degree of freedom system, for example. Okay, but we are going to use also our equivalent static force method to say that there is force is going to be applied on the structure relative also to the masses here. This concept results in equivalent static forces being applied at each story level, and for many buildings produces reasonable structural design. And this is an important issue. For many buildings produces reasonable structural designs. This means that there is an engineering judgment here that should take place, that we found that the previous designs of the previous buildings, they survived earthquakes. This means that our strategy, our approach is okay, it is right. So this is why we said that from the practical point of view, equivalent static force method is highly acceptable method. It should be noted, however, that there are structure configuration for which ASCE 7 will require the use of an analysis method more sophisticated than the equivalent lateral force procedure. Yes, we have response spectrum, as we are going to explain later. We have time history approach, time stepping. We call it time stepping or time history, and we have nonlinear time history response analysis. Okay, for special structures, which is exceeding certain limit in height or exceeding the regular conditions stipulated by the guideline. Now let's talk about the philosophy of design and detailing. The empirical forces given in the equivalent lateral force procedure are considerably lower. Look to this point, lower. This word is very important. Than that would be expected in major earthquake. Well, it is a big question mark here. So why we are using this approach? Because we are going to have lower loads. So what is the point here? If this empirical force is going to be produced by our equivalent static force is going to be lower. The answer in the next point, which is the key to this singular philosophy, lies in design and detailing. Remember that well. These are like two conjugates that you need to take care of. Design and detailing of the structure so that there is sufficient system ductility. This is very important, as I explained it in the previous videos. Do you remember the previous videos that I was talking about ductility issues and explanation of it? So detailing and design is directly related to ductility. For the building to remain structurally safe when forced into the inelastic range in a major earthquake, whenever we have lower forces and whenever that we're going to make proper detailing, our structure is going to be forced into the inelastic range, and there is some performance or some nonlinear performance of the structure. This detailing and the design as well, they are going to maintain our structure to be safe, okay, during the inelastic range. That's the philosophy that we have. This is why we said that ASCE is not all about loads. It is also about detailing as well and configurations. Okay. Therefore, in areas of high seismic risk, detailing requirements apply to all of the structure building materials, including steel. Okay? So whenever that we're talking about detailing, what is the meaning of detailing? The term detailing here refers to special connection design provisions and to a general tying together of all lateral force resisting systems so that there is continuous path for the transfer of forces from the top of the structure down into the foundation. What is the meaning of this word? Detailing means that we are going to use special connections to secure something that is very important, that the continuity of our lateral force resisting system, okay, and holding them together with the gravity loading system of our structure, and there is a continuous path for the transfer of forces. Do you know that whenever that we have a building and we have forces coming in it, we want to be sure that there is a continuous path, okay, that is for the lateral resisting system, safely would transfer it to the ground. So if there is no discontinuity, then we are not going to face any failure mechanism. That's the point here. So the detailing is securing this point for us, is securing the continuity and the transfer of forces, okay, to the foundation through our system, through the LRFS. Okay. Now let's talk about the seismic provisions, some details about the seismic provisions. Whenever that you open, you're going to open this ASCE 7, you're going to find that chapter 11, starting the, we can say it is the start of the seismic provisions, chapter 11. And you are going to find some some definitions, symbols, and so on, until that you reach to the first part, which is 11.4, first section, that is really concerning us. Okay, you're going to find here something that is the start. Let's say that this is the first thing, okay, of understanding where are we. We are going to start from the earthquake, where it originated, from where it did originate, and how we can put our building from the source of the earthquake and where we can put it. So whenever that we are talking about the seismic ground motion values, which is the title of this section, we need directly to go to this title, which is fault, the faulting. We need to know where our building is. If we have a fault, do you know that from the previous videos I explained about the faulting and the source of the earthquakes and so on, and the propagation of the waves. So if we have the epicenter of an earthquake, and we have our building that is near to it within specific distance, then there is some additional requirements are needed. And we need to think about it, and we need to consider that in our design. So first of all, let's know what are the limitation of the distance, and second, let's know what is the significance of being near to the seismic source. They put it in this way: near fault sites. Near fault sites. So this means that if there is the word near here, this means there is far fault sites. Yes, that's right. We're going to categorize building distances whether they are near or far. But the problem is, the point is, for the far, there is no problem. All the details of this guideline works well for it. Okay? But for the near fault, we found and realized that it needs additional requirements. This is why you will find that this section is new. It is in ASCE 716, but in 10, for example, it was not there. In 5, the previous editions, it was not there. Okay. So we are going to categorize them as two categories. The first one, the near fault sites satisfying either the following conditions shall be classified as near fault. One of them. Okay. Either this, okay, yes, either of the following conditions, either of them, okay. So if it's within, if the building within 15 kilometers of the surface projection of the known active fault capable of producing moment magnitude of magnitude 7 or larger events, or 10 kilometers, but the site or the fault is capable of producing MW6, which is magnitude of 6 or larger. Okay, so we are like, these are the like conjugates. Okay, 15 kilometers with 7 or larger, or 10 kilometers for producing 6 or larger events. Okay, so okay, this is the definition of it. But what is the implication of it? Why we need to consider these near faults? We found that for the near fault sites and the buildings, when they are experiencing earthquakes, we found that these buildings, they experience what we call it impulsive characteristics. Impulsive characteristics means that the building, whenever that the earthquake is going to start to work, it will make something like this and then go back like this. A very huge magnification in the amplitude. This makes a kind of destructive impact on the structure. This cannot be found in the far fault. If it's far fault, we're not going to find this impulsive kind characteristic. Another thing, we call it directionality effect or directionality effect. What does it mean? Whenever that we have I'm going to talk about this issue in detail, okay, later, but I'm going just to give a hint about what is the meaning of it. Whenever that we have a source of earthquake here, and we have a building here and another building here, which is away from this source with the same distance, but the source is opening or progressing in this direction. This is what we call it directionality effect. The waves that is going to come to this building is going to be different than the waves that is going to come to this building. And this is what we call it directionality effect. You are going to find that here in this one, the amplitude of the waves is going to be higher, something like this. The amplitude is going to be higher. However, here the amplitude is going to be lower. Okay, it is going to be lower amplitude. I'm going to talk about this in detail, so do not worry about it. I want you to know the two implications here, that we have impulsive characteristic and directionality. They are highly destructive, particularly destructive. Okay, then what is the consequences? What we're going to do for this? Actually, whenever that we know that this is a near fault site, then we need to take care of selection and scaling of the ground motions that is going to be used in nonlinear response history analysis, and for the design of structures using seismic isolation and energy dissipation devices. So these are the two consequences that is going to be related to the near fault sites. Okay, selection and scaling. We're going to talk about this in detail later. So there are two main things here: selection and detailing of the ground motion for nonlinear response history analysis. Okay, so now this is the near fault, which is the first section that you're going to see in the code or chapter 11. Okay, now let's go to the first thing. After that, you're going to see, which is the mapped acceleration parameters, which is S sub S and S sub 1. Do you remember from the previous lecture I mentioned about the response spectrum, and I mentioned that we can draw the response spectrum, right, which is something like this. So in order to draw this response spectrum, which is going to give us what is the acceleration that the building is experiencing during an earthquake, we are in a great need of two important parameters that going to help us in constructing this response spectrum. Okay, these parameters, we call them S sub S and S sub 1, which is spectral acceleration mapped. Take care, the word mapped here. Mapped acceleration parameter, or the mapped spectral acceleration, at short period. So S stands for short and 1 stands for at 1 second. So we're going to give some value at short period S sub S and another value at S sub 1. Okay, so they are two parameters. S sub S and S sub 1 play a key role in the determination of ground motion values used in seismic design. These are derived using the maps, so we are going to have maps given in ASCE. You can check these maps by yourself. Chapter 22, we're going to find the maps, okay? Or by accessing the web-based information, you are going to find a web-based information giving this, which is related to the USGS. If you go to this website of United States, GS, you're going to find that they are providing these values, okay? The seismicity maps showing the contours of 5% damped, 0.2 second, this is the short period, okay? This is the first, this is what we call it S sub S, and 1 second, which is, we call it S sub 1. Spectral acceleration values for MCE. MCE means that maximum considered earthquake, but we call it risk targeted. It is risk targeted R, okay? They are different actually than the previous versions of 2010. Starting from 2010, we are using risk targeted MCE, maximum considered earthquake. Okay, what is the significance? I'm going to talk about it in a minute. Okay. The seismicity maps can be found in chapter 22 in ASCE, as I said, where S1 is less than or equal. Yes, this is only a kind of important thing for us. In order to say that a building is going to be designed based on the guidelines in ASCE or not, we need to check something very early on, which is S sub 1, okay, and S sub S. If S sub 1 is less than 0.04 or S sub S is less than 0.15, then the structure is permitted to be in seismic design category A, which that you do not understand or do not know now, I know, but it seems that as if seismic design category A seems like that we are not going to design the building for seismic, okay? That's the meaning of it. So this is, we are going to deal only with the structure as if it is like having only very small lateral force, and that's it. We are not going into the details of the seismic loading and seismic force distribution and so on and so forth, okay? So this means that if our S sub 1 and S sub S, they are very small, this means that our structure is not going to be designed for seismic loads only. It is going to take a small portion, which is like 1% of the weight of the building. That's it, and we can design the structure for it, okay? Now, let's go to the next point. Why we have chosen point S and 0.2 seconds and 1. Why this is representative for short periods, this one is representative for long or for longer periods. The rationale actually here that 0.2 seconds is reasonably representative of the shortest effective period of the buildings and structures. So if we're going to talk about buildings and structures, so 0.2 seconds is considered to be like the 0.2 seconds is reasonably representative of the shortest period, because if you are going to draw the response spectrum, you're going to find that it is almost here, which is something that is very short, and the structure is very stiff in this case. The spectral response acceleration at period other than 1 second can typically be derived from S sub 1. So this means that 0.2 is representative of the shortest period available, and 1 second is considered to be a reasonable assumption to derive from it any kind of longer period structures. Okay. Consequently, these two response acceleration parameters, S sub S and S sub 1, are sufficient to define an entire response spectrum. You're going to see now, to draw this response spectrum, I'm going to give some portions, and each portion is going to be defined based on S sub S or S sub 1 in some way or another. Okay, so they are sufficient for us. Are sufficient to define an entire response spectrum for the period range of importance for most buildings and structures. For most buildings and structures. Now let's talk about the word that I have said before that we are going to talk about it later, the risk targeted MCE, maximum considered earthquake. Okay? The risk targeted maximum considered earthquake, MCER, ground motion is the most severe earthquake effects considered by ASCE 7. IBC actually in chapter 16 it refers to ASCE 7. Okay, so they are like sometimes they are interchangeable, but anyway we are going to refer to ASCE. This is International Building Code, chapter one chapter in this code, which is commonly chapter 16, referring to ASCE 7 for seismic design. So we use now the word risk targeted. Okay, what is the point? What is the rationale behind this? The basis for mapped MCER ground motions in ASCE 10 is significantly different from that of the mapped MCE only ground motion in ASCE 5. So from 10 and 5 there are a great difference between the two and previous editions of ASCE. So this ASCE 710 is considered a new era in the way of understanding the maximum considered earthquake. Okay, it is going to be based on risk targeted, not only based on the uniform hazard. Okay, I'm going to talk about this now. The probabilistic or MCER, maximum considered earthquake risk targeted, probabilistic ground motions are based on, look to this point, uniform collapse risk. A uniform collapse risk. 1% probability of collapse in 50 years. Rather than a uniform hazard of 2% probability of being exceeded in 50 years. What is the meaning of the both? Actually, before ASCE was telling like this, that all areas in the United States, for example, they should be exposed to uniform hazard. The probability of exceedance of this hazard should be 2% in 50 years. But there is something that is not taking into consideration here, which is the safety factor, the inherent safety factor inside the building. We do not know what is the capacity of the structure itself. So maybe we are going to use uniform hazard, but the buildings, they are different in their safety factors. So the collapse probability for each building will be different. Okay, this is the rationale here. So now we started to say, well, this is not right. We need to use another philosophy, which is uniform collapse risk, that is going to take into consideration the hazard uniformity and the collapse uncertainty of the buildings. The collapse uncertainty of the buildings. The assumption is that buildings designed in accordance with ASCE 710 have a collapse probability of not more than 10% on average if MCER ground motions were ever to occur at the building site. That's very important here. 10%, which is, as we said, it is the 1% in 50 years, almost around 10% on average. Okay, let's explain about this approach, why we abandoned ASCE 7, why we abandoned the uniform probability of hazard. As explained in the commentary, you are going to find this in a commentary of NEHRP 2003 provisions. It's very detailed. The topic is very detailed and very nice for anyone to read it. ASCE 7.5 approach provides a uniform likelihood throughout the nation that ground motion will not be exceeded. That's the main idea here. Ground motion is not going to be exceeded within a specific period of time, which is 50 years. But it doesn't provide for a uniform probability of failure for structures designed for that ground motion. That's the main idea here. This is the main shortcoming of ASCE 7. It doesn't consider for the probability of failure. Then there are significant variations in the probability of collapse because the uncertainty in the collapse capacity or factor of safety, this is factor of safety of the building, against collapse relative to the ground motion for which the structure is designed. Yes, maybe we have a structure designed for safety factor of 1.5, other structure for 1.2. If both are going to have the same probability of hazard occurrence, then this probability of failure different than this probability of failure, and which is not right. We do not want something like this to happen. So in this regard, ASCE 710 started to take into consideration the uncertainty of collapse of structure and the safety factor of design. Okay. So these variations are particularly significant between locations in the western, like California, for example, versus central and eastern United States. And this is very true, okay? Because the margin of, or the safety factor is different actually from the buildings itself and from the location and the area of the building itself. So based on that, we need to take into consideration the safety factors of the buildings in different areas. Okay. So this is the rationale of risk targeted. Okay, now the site coefficients FA and FV. Whenever that we are dealing with an earthquake that is going to happen and it has a source, if we have the ground here and this is the source of the earthquake and we have the building here, for example, the waves that is going to approach to this building would go through different soil deposits, right? So we are going to find that we need, if this is the waves of the earthquake, we found that the surrounding soil underneath the building has a great significance on the response of the structure itself. This was evident in Loma Prieta earthquake in 1989. They found and recording something that is very unique. They found that for soft clay, whenever that they have structures with soft clay underneath and other structures with rock underneath, they found that soft clay sites relative to rock were extremely high. The impulse or the magnitude was extremely high, ranging from 3 to 6 times, even that with the same earthquake and with the same distance. But they found that the soft clay is magnifying the earthquake waves like 6 times. So this means that we need to consider the soil condition underneath the structure. Based on the analysis of these strong motion recordings, ASCE has provided values for soil condition. Now we are taking into consideration the soil condition. In ASCE, we are going to have a set of 6 site classification, starting from SA to SF, based on the average properties of upper 100 foot or 100 feet of soil profile are defined in ASCE. And find it. Since in practice geotechnical investigation are seldom conducted to depth of 100 feet, ASCE 7 allows the geotechnical engineers to determine site class based on site-specific data, which is the geotechnical report that you needed, and professional judgment, Okay. Now, when the soil properties at a site are not known in sufficient detail, then the ASCE allows you to assume it to be at class D. So if you do not know the soil details of your building, then you can assume it to be class D, unless geotechnical data indicates that class E or F soils are likely to be present. In this case, take care that you need to go with the geotechnical data. Okay. Likely, it is likely, okay, that this is important. This is important. It is, they are not sure, okay, but in this case, if you do not have any information, then you can assume it as class D. In general, softer soils with lower shear wave velocities exhibit greater amplifications than stiffer soils with higher shear wave velocities. So we should take care of the type of the soil underneath your building. If it's soft soils compared to the stiff soils, take care that there is magnification of the earthquake waves and amplitudes. Increased level of ground shaking result in increased soil stress strain nonlinearity. That's a very important concept. I'm going to explain it in a minute based on the tables of FA and FV. Increased level of ground shaking means that if we have increased level, means that our ground acceleration, which is EAG, the ground acceleration is high. They found that increased soil stress strain nonlinearity is going to take place. Do you see that? Do you understand it? When you can understand it whenever that you have like a piece of or if we say that we have soils, and these soils, they are going back and forth rapidly and quickly. They are going to experience nonlinearity, and this nonlinearity will lead to what? Exactly, soil damping. There is energy dissipating here. It's natural energy dissipating phenomena that is going to take place because of the nonlinearity of the soils. In general, reduces the amplification. This kind of damping reduces the amplification, especially for shorter periods. For soil deposits of sufficient thickness, soil amplification is generally greater at longer periods than shorter periods. This is another hint that need to be maintained also in our mind. Now this is, you can find this in ASCE 10. These are the tables for FA, call it the side coefficient. This is a table for FV, for also side coefficient. Actually FA, it is for this is the for short period, okay, for short period, and the subscript here A, it is for acceleration period. Do you remember when I was talking about there we have like different regions? The first region is acceleration sensitive, this region is velocity sensitive, this region is displacement. So we're talking about short periods, so we have FA here, and here it is FV because it is longer period, so it is related to velocity. Okay. Anyway, this is the mapped risk targeted maximum considered earthquake spectral acceleration response acceleration parameter at short period. So this is, we're talking about S sub S. Here are going to find S sub S, and they are putting it based on some values here, and these are the 6 different soil starting from A, B, C, D, E, and F. And if you go here, you're going to find that whenever that we go to the left, you're going to find that the values are decreasing. This means what? That this FA, we are going to use this FA to multiply it, okay, by the S that we got it from the map, S sub S, for example. So whenever FA is larger than 1, this means that we are amplifying the mapped spectral acceleration. If it's less than 1, this means that we are reducing it. So for example here for site class A, you're going to find that it's almost like 0.8 for all of them. Okay, this means that we are reducing the amplification. But if it is site class E, then we are going to magnify the amplification. Look, 2.5, almost between double and triple the amplification. But if we have short periods, okay, S sub S is smaller or smaller than 1.25, for example, it is going to be, as you can see, 0.9 here. And if it's like smaller than 0.25, means that it is very, very small, then we're going to have a very high amplification factor. If S sub S is large, then we're going to have maybe 0.9, okay? Okay. Then in the same case, we are going to look to each one here, S sub S. If we have the soil class, whenever that we go stiffer here, this means that we are having amplification factor that is higher, okay? That is that is higher. Okay, and this is similar for FV as well. We can put these notes here. It worths while to note that the factors FA and FB in tables are all equal 1 for site class B. This is right because it is recorded for default values, which is 1 for all of Y, because it is considered that the soil to be A or the site class to be B. For this we do not make an amplification or reduction for due to the site class, but for other type of classes we need to consider it. Okay, so this is only an assumption. This is because the spectral acceleration given in the intensity maps were all determined for sites classified as B. That's it. Note also that the amplification factor for soft soils may be as large as 2.5 for short periods and as much as 3.5 for longer periods. We are talking about soft soils, okay? Maybe as large as 2.5 and for short periods, and as much as 3.5 for longer periods. Let's go. Look here, this 2.5. We're talking about soft soils, okay? And here it is 3.5. Take care if V, this is factor for 1 second. Okay, and this is for short period. This is long period, this is short period. Okay, so this is 2.5 here. Look, the maximum here, it is 3.5. Okay, so for longer period, spectral acceleration, okay, we are going to have higher amplification factor, which is 3.5 compared to 2.5 here. Okay. Furthermore, note that the amplification factors considered are less for large spectral acceleration than for small ones. That's right. For large, here, whenever that S is small, and here we are going larger, right? So in this case, you are going to find that it is what? Decreasing, as you can see. Started 1.7, 1.5, 1.5, 1.4, 1.3. So it is like as if decreasing here. Okay, this is the second comment here. Okay, the code recognizes thus that under large spectral acceleration, soil may incur into their nonlinear range. The philosophy or the hint that I have mentioned before, that whenever that there is large spectral acceleration, there is nonlinearity would take place. This means that what will happen in this case? Yes, it will decrease. It will decrease if the amplification would decrease. There is like energy dissipation here. Okay, nonlinear, and that is the nonlinear behavior inhibits resonant effects and ground motion amplification. That's right. Okay. This is ASCE 16. Okay, this is the latest one, and you're going to find that at B, actually the factor is not 1 anymore. Okay, there has been some modifications. Okay, so take care which version that you are going to use. We recommend using the latest version always. Okay, but in general, the whole table, it is going to be the same. Okay, they are going to be similar to the previous one, and ASCE 10 and 16, they are almost similar. Okay, after obtaining the FA and FV from these tables, the previous tables, what we're going to do is we are going to get what we call it maximum spectral acceleration. Maximum here means that due to the effect of soil. So we are going to say that S maximum for short periods would equal to FA times S sub S, which is already we have obtained from the maps. Similarly, S maximum at 1 second period at 1 second period is going to equal FV times S1, already obtained from the map. Okay, so these are S sub S and S sub 1. It is MCR, risk targeted, from the maps, as we have explained before. So this means that our FA now, so SM for short periods would equal to FA from the previous table times S sub S. That's it. And for S maximum for 1 second equal to FV times S sub 1. That's it. This is the maximum spectral acceleration. Okay, we call it maximum spectral acceleration, and it contains, or it includes what? This, considering the soil effects. So if I ask you what is the difference between the maximum spectral acceleration and the mapped spectral acceleration, which is already, I have put it here, this is number 1, mapped. So the difference between the two is the inclusion or the effect of soils, okay, which is going to be considered using FA and FV in the tables, okay, that we are explaining, table 11.4, 1 and 2. Okay, now this is regarding the maximum spectral acceleration. Now let's go to the third part, which is related to the design spectral acceleration. We are at the last stage needed for obtaining two parameters that is going to help us for constructing the response spectrum. So in this case, we are going to put SDS, which is design spectral acceleration at short period, would equal to 2/3 times the previous SMS that we have obtained. And similarly for SD1, it equals to 2/3 times SM1, as you can see here. This is SM1, this is SD1. Okay, so we are dealing with this. So now, what is the meaning of this? Design spectral acceleration parameters are considering design consideration. So the design spectral acceleration are taking into consideration some design effects. So what is the rationale of this 2/3? I'm going to explain it here. Actually, it's a little bit, it's a long story, but I want to summarize it. They found that whenever that they are designing some coastal buildings, some buildings in California, in the western United States, they found when they used the design response spectrum, they found that their structures are having 1.5 safety factor against the maximum considered earthquake. But when they go to another place like New Madrid, for example, they found that this safety factor is not going to be maintained. The design response spectrum, if we say this is the design response spectrum in California, for example, and this is the maximum considered earthquake or maximum considered response spectrum. This is in another place. Let's assume it's New Madrid, another place. This is the response spectrum. And here, this is the maximum considered response spectrum. What is the difference between here? This is California. They found that the difference between design response spectrum, which is the small one, and the maximum considered response spectrum, it is small. Then the safety factor here is going to be 1.5. I mean, our structure would have safety factor of 1.5 if maximum considered earthquake occur. But in New Madrid, they found that if we design to this design response spectrum, the safety factor when a maximum considered earthquake occur, it will not even reach 1. It may be 0.9, so our structure would fail. So they found, well, it is not right to use the design response spectrum directly. We should put the maximum or the mapped based on the, in the maximum risk target. Okay, and from it, we can multiply by 2/3, which is the common safety factor inherent in our buildings. Okay, so that's the, you can read this here. I put it here from one of the references. But what I have explained now is telling us the story. Okay? So in order to summarize, we can say that this safety factor, which is 2/3, is introduced to account for assumed inherent level of building overstrengths. That's the summary of it. Okay? Building overstrengths. Because we, as I said, that the risk targeted, if we are going to use the risk targeted, we found that we have safety factor of 1.5, including the details and everything. So this means that we are going to reduce this acceleration or the design or the spectral acceleration to be 2/3 only. Okay, so the maps are considering are giving for us the maximum, the mapped acceleration, spectral acceleration. It is based on rare earthquake, the maximum considered earthquake. But in our design, we need something related to the design. We found that the level of design for us is giving safety factor of 1.5 in this maximum considered earthquake. So we are reversing the issue. We are going to multiply by 2/3. Okay. Okay. I think this is the end of this video. Next video, I'm going to talk about some examples. As you can see here, this is the next video. The main slide or the title slide. I'm going to talk about some examples about ground motion parameters and how to construct the design response spectrum. Okay, thank you for listening and see you in the next video.